Hi guys, this is Hadi Atai. I'm going to give you an overview of the NLP and natural language processing. It's the number one lecture from the series of lectures that I will be going over. Slides for this lecture is borrowed from a Stanford CME 295 course. And let's get started. We'll be, using a lot of abbreviations, but don't worry. So we'll get to each one of them separately. And, we have abbreviations with transformer-based models. We have training strategies, data sets, metrics, tasks, and miscellaneous architecture and techniques. I'll do basically a rundown of what we'll talk about today. And we have an NLP, we'll do an NLP overview before everything else. Then I'll talk about tokenization. Then we'll talk about word representation, RNNs, self-attention mechanism, transformer architecture, and then we'll wrap it up with a end-to-end example. In terms of the NLP tasks, we have a number of NLP tasks. The first one is classification. Obviously, you're gonna have an input text and classifying it in different formats and examples. It would be sentiment extraction or sentiment analysis. We also have the intent detection, language detection, what language the input text is in, and then topic modeling. We also have a multi-classification, which instead of, classifying the input text as a whole thing, as one thing, you could be classifying every word. Like examples of it would be part of a speech tagging, and named entity recognition, dependency parsing, constituency parsing, etc. The other one is text generation. So you have an input text and the model will generate some output. Examples of this are machine translation, question answering, summarization. So you provide an input text and the model summarizes it for you, and text generation. Any other text generation would be, I guess, under this category. So if you have a sentence as an example, this teddy bear is so cute, the model will should actually classify it as a positive statement. So this is an example of a sentiment analysis. So it could be used on data sets like Amazon reviews, IMDb critiques, Twitter, X.com. The evaluation metrics for the classification tasks is accuracy, which is number of observations that were correctly predicted, precision, which is the percentage of predicted positives that were correct, and recall, which is actually the percent of actually positives that were correct. You also have the F1 score, which is a score that is a function of precision and recall. An example of named entity recognition is basically the model will take an input text and will tell you which part of the input is the named entity and recognize it. I guess it is used on annotated Reuters newspaper data sets like the ones mentioned here, CON-LL 2013 and CON-LL++. The same metrics can be used for this multi-classification task. In terms of the generation task for the model, an example would be translation, and which is, you see an example here. The English sentence is translated to French, The data sets, you have multiple data sets right now, but the one most commonly used for training purposes and testing is WMT14 English French and WMT14 English German. The reason these two are used because it is a nice way of comparing your model to the others, and because most of the research is tested on these two models, and you can compare it. And the metrics, we have the blue metric, which is the quality of text translated. It's similar to precision. You have the rogue metric, which is the quality of text generated, and it's similar to recall. You also have the perplexity metric, which is going to quantify how surprised the model is to see some words together. In terms of the history and the timeline of how everything came about, the recurrent neural network, which is the foundation of the natural language processing, was introduced in 1980s. It had a fundamental flaw, which was kind of mitigated by the long short-term memory, LSTM, which was introduced in 1997. And in 2013, Word2Vec paper was published. 2017, transformers were introduced, and 2020s, it was when large language models were basically introduced. And what enabled, the recent progress, dramatic shift in terms of success of the large language models and natural language processing in general is, first of all, the lots of data that became available, and the growing computing power, and also introduction of the TPUs, tensor processing units, and which also enabled the researchers to be able to iterate on different ideas quickly. Next thing is tokenization, a fundamental topic in natural language processing. For instance, we'll stick to this example of cute teddy bear is reading for the, throughout this slides. When you want to take the sentence apart into units, I guess we have an arbitrary way that is shown here. We have teddy bear being a unit, is reading, and other words being also a single unit or a token. We have the word level tokenization, whereby every word and every punctuation is considered to be a token. We have the subword level tokenization, which is technically, subword is a language unit smaller than a word, which either has its own meaning or adds meaning or kind of changes the meaning of other words. So any prefix or suffix would be considered a subword unit, as well as the punctuations, like the ing in reading is a subword unit, whereby in a word level tokenization, reading would be considered one unit. Below subword tokenization is the character level tokenization. And as you can see, every character, whether a space, punctuation, or anything else, would be considered a token. Each one of them have their own pros and cons. Word level, it's simple and interpretable. The risk is that you could have words that are out of vocabulary, and also does not leverage knowledge of root, which is present in subword level. It can use the knowledge of the root to derive, whether derived new words or find out if the two different words kind of related or not. Subword level also leverages common prefixes and suffixes, as I talked about, and it's learned from data. Some examples of subword level tokenizations are word piece and byte pair encoding, or BPE. For character level tokenization, there is a smaller chance of out of vocabulary risk. And I'll forget to mention that in subword level tokenization, there is still a risk of out of vocabulary risk, but it is significantly less than in the word level tokenization. In character level, there's it's robust to casing and misspelling, obviously. Computations is slower because you're dealing with the smaller units, and embeddings is not interpretable. Now we get to word representation. There is a, how you represent words, because computers do not understand words. They understand numbers, and we need to convert words into numbers, and specifically vectors or matrices. One naive way is one-hot encoding, which is basically based on the size of the vocabulary. You have a vector which is the same size as the vocabulary. And for each word, you have one element that is hot, or one, basically. So every word with respect to another word in a n-dimensional, I guess, coordinate system, which has n words in the vocabulary, they are not related. You cannot find any similarity between them. There's a way of measuring the similarity between words, which is called cosine similarity, and it technically measures the distance between the vectors that each word creates. And as you can see here, all the words here that have a vector that is perpendicular to the other one. Therefore, the cosine similarity for all of them with respect to the other is 0. Now here we're dealing with a 3-word vocabulary, but if we have an n-word vocabulary, 1,000-word vocabulary, the same thing will happen. We'll have an n-dimensional space, and all the words are perpendicular to one another. The other one which is called a learned embedding, and it kind of learns from the data instead of just assigning a one-hot vector to each word. Therefore, we have words have a level of connection to the other ones. So, for instance, in this 3-word vocabulary, the first element is for soft, the third, and all the words we have is soft, teddy bear, and book. The first element belongs to the word soft. The second element belongs to teddy bear, and the third belongs to book. As you can see, obviously the first element, this is a vector for word soft. The first element is 0.95, which is, soft is very similar to soft. The second one is how related or similar is soft to teddy bear, and which is, we have 0.32, which means there's a quiet the relationship between these two words is not insignificant. And for soft and book, we have 0.01, which means they're kind of totally unrelated to one another. And if we take the cosine similarity between these two pairs, like teddy bear and book, we have 0, and then teddy bear and soft, we have something almost equal to 1, which means they are very similar, and maybe in meaning or in something. So these two are, two ways to represent tokens or words. The other one is word2vec, which was, as I said, a paper that was published in 2013. It technically is a neural network with a proxy task over billions of words worth of text, and its job is to learn an embedding layer via these, a number of proxy tasks. The two major ones is the CBOW, or continuous bag of words, where you have the words before and after a certain word or a phrase, and its job is to predict what comes in between. So here its job is to predict the teddy bear that's come between acute is reading. A skipgram is the opposite of continuous bag of words, and its job is to given a word or a phrase to predict what comes before and after. So here teddy bear is given, and its job is to predict acute and also is reading, which comes after it. And by these proxy tasks is able to create this embedding layer that is used for different purposes. The way the architecture works for word2vec is that so you have a input layer, hidden layer, and output layer. Input has size v, the hidden layer has size d, and output has the same size v as the input. So how it works is that, let's say you have the beginning of a sentence where the word A is fed into the input network, and the word A has this vector represents word A 10000. Then it is multiplied by the hidden layer, which is this is what has already been learned. It is multiplied by this matrix, and the result is this matrix, which technically gives you the after a softmax activation gives you a series of probabilities. The highest probability goes to the second word, which is cute, and therefore it predicts that cute is the word that comes after A. Now in the next step, cute is fed into the input layer, and its job is to again multiply it by the hidden layer, predict what comes next after the word cute. So the cute has a different word embedding, which is 010000 multiplied by the hidden layer, and a series of probabilities is generated. Based on that, the next word is predicted. Sometimes there's more than one option. And teddy bear is the next input and is going to predict what comes after teddy bear, what comes after is, using the same process. By learning these over a large body of text, it is able to find correlations between different words and phrases. So it will learn that teddy bear is soft and Persian poetry is a form of art, and all these relationship is then generated through this process. Now I quickly talk about RNNs. As I said, it was first introduced in the 80s, is a class of neural network where connections form a temporal sequence, meaning that as you can see in this architecture, every word, so these X's are the inputs, and A could be the beginning of the sentence, and there's a hidden layer in the middle, the blue ones, and each cell in the hidden layer is connected from an input layer element, and it outputs something. It doesn't necessarily have to output, every one of them have to output something, but it has the option to generate an output. And the connection is that each of the hidden layer elements is also fed to the next step. So we have different time steps, 1, 2, and then T and T plus 1. So element T takes the input from the hidden layer at t-1, also the input at t, and itself is also fed into the next step at t+1, and this continues. So here the word A is fed into the network, the word cute is generated, but this network that is somehow calculated is also used as an input to the next hidden network element. But also the next word in the input is also fed into that particular element in the hidden layer. So it's supposed to predict the next word, which is teddy bear, or if it predicts it correctly. So the process continues, is reading, and that's it. So the way, if you want to think about the 3 different tasks that we talked about, if the job of the model is classification, the only output we have is after the last element of the input and the hidden layer. So this y hat is predicted, whether it's, predicts the input as something, sentiment analysis or whatever. If it's multi-classification, each one of these hidden layer elements will output something, whether it's a part of a speech tagging or something else. And if it's translation, after everything is processed, the entire sentence has to be processed before some output is generated. Therefore, you can see it starts generating the output after some time, maybe at step L here. So this is the different ways that the RNN is responding to each tasks. So there is some problem with RNNs, some fundamental problem is what is called a vanishing gradient, meaning that this element right here at the end does not remember what was in the beginning. So it only deals with the element immediately before it, and also the input layer. So anything in the beginning is not does not affect the elements in the towards the end. But something architecture called long short-term memory was introduced in 1997, which was technically going to mitigate that shortcoming of the RNNs, and its job it was to kind of make the model remember every element, even from the beginning of the sentence or the inputs. You can see in the architecture that each input is fed into all these elements in the hidden layer. So therefore, it is able to, kind of relate every element from the input to every element in the hidden layer. So it kind of mitigated that problem of vanishing gradients to a great extent. So, kind of summary of obviously a non-exhaustive list of, main methods. The word2vec with two examples that we talked about, CBOW and Skipgram. It's very simple yet powerful, intuitive embeddings. The disadvantage of it is that the word order does not count in word2vec, and embeddings not context aware. In recurrent neural networks, word order matters because we read the input in sequence, and it also brought state-of-the-art results. But it also has a vanishing gradient problem, and the computation is quite slow for its time. What's changed everything for the better was attention that was introduced in 2014. The translation tasks had a real issue with long-term dependency, especially for long sentences. It wasn't doing so well. And also sequence to sequence, unable to remember what input sentence was saying. So that remembering things was the main fundamental problem. And the attention architecture was telling you, kind of helping with these problems. So every element in the output is aware of every element in the input. So that's the word attention is coming from. So even the last element in the output is kind of, aware of what's happening in the input, all the element, not just that, end of the sentence or the last sentence in the input. So knowing that, the word lit in French is the same thing as reading, is enabled because, the awareness of what is happening for every element in the input sequence. And the paper Attention is All You Need was, published in 2017. It relies on self-attention mechanism, and it brings a state of the results on machine translation tasks specifically. So, meaning that the word teddy bear, when it is being read by the model, it not only reads the teddy bear, but every other word that is in the input sentence. Thus, the word self-attention. And also, I guess the word attention also is it's basically attending to every word in the input sequence. And it also has this concept of query key value. Every element is treated as a query, the query of teddy bear, and it basically reads or looks at every key in the input, and the T here is basically it is saying that it's a transpose matrix. The key of A, cute teddy bear, is reading, and dot, which also give you a value vector for every input sequence or every input element. Now the softmax of the whole thing basically is just doing a simple computation with matrices. So it's kind of efficient dealing with these because all of them are matrices, whether it's a query, key and values, and divided by the dimension of the keys. Here it kind of shows the architecture of what it does. Query, key, and value are fed into the model like that. And the output is after a linear activation function, is a multi-head attention. And the reason it says multi-head, it's basically saying that everything is being done in parallel, just like in convolutional neural network where you apply multiple filters. It is happening in the same way. So now we'll talk about the transformer architecture. It has attention, self-attention, which is an encoder, encoder, decoder, decoder. What does it mean? So if you look at this here, right here, it is decoder part, and this is this is the encoder part, And this is the decoder part, meaning that the input is being encoded and at the end it being decoded into the new language. You also have a feed-forward neural network right here at the end of both the encoder and decoder. And you have a positional encoding right here. So the input embedding, the text, first of all, the text is tokenized. Then there is learned embedding for the tokens. That we have a vocabulary size that the model is aware of, and then the dimensionality of the model, which is technically the embedding dimensions. Why do we have a positional encoding? It's basically a trick because the model is not aware of the position of the elements and the tokens. So there is one element here called positional embedding, positional encoding, that kind of keeps track of the position of the tokens. It can be either learned or hard-coded depending on the model. So it basically, its job is to understand relative input position. So basically, wants to know where each element is with respect to the other elements. So this part, which is the encoder, it has an encoder attention, self-attention right here, has a feed-forward neural network and a normalization layer at the end. The parameters that it is dealing with is n, which is the layers stacked on top of each other. H is a number of attention heads, basically the level of parallelization. The size of the feed forward, the size of the key, and then the size of the value. You also have the D of the model, which is the embedding dimensions. The output embedding right here is basically learns, learns embeddings for the output tokens. In practice, it starts with the beginning of sentence during translation. So every time it sees that token, the beginning of sentence, it knows that it's the beginning of the translation. It has a vocabulary size V and then embedding dimensions D underscore model. Inside here, it's something is interesting happening. The decoder attention, it says masked multi-head attention here because it only looks at the words that has already been translated. So it doesn't look at the entire thing, obviously, because it hasn't been translated. But the second part, it looks at everything, whether it's has been already translated or not translated. We also have a normalization layer. N is the layers, number of layers stacked. H is again number of attention heads. D, FF, D key, D value are the sublayer dimensions, and the D mile is again embedding dimensions. Then at the end we have a linear projection and also a classification problem that outputs the probability of belonging to a class, where class is actually the word itself. So regarding these, I talked about the multi-head thing, and basically the idea is that we run multiple self-attention layers in parallel. What are the benefits is that it helps the model to capture the different attention features in parallel. Also, it helps compare maybe different results to each other. And it's similar to the convolutional neural network in computer vision, where you have multiple filters applied. There's also another concept applied here, and that's called a label smoothing. And the idea was introduced in 2015 vision paper, and the confidence is bad. Overconfidence is bad. Why is overconfidence bad, especially in natural language processing? Because I'll give you an example. When you have the word like acute, uh, teddy bear is not the only option that can come after acute. You could have a cute story, a cute car, a cute dress, a cute puppy. All these options are, completely valid. So by just sticking to one option, it's not good for natural language processing. So this label smoothing enables to have, instead of having a delta here, it kind of adds this epsilon value that says, don't be so confident. Maybe that option is wrong, the option that the model is predicting. So by saying that the predicted value is wrong, could be wrong, it leaves the room to look at other options that could be available. It's basically a general techniques that prevents overfitting, and overfitting is a problem in any machine learning model, and overall it improves accuracy and blue score. Now we'll end this with an end-to-end example. The same sentence, a cute teddy bear is reading. We start with that. We add the beginning of sentence and end of sentence to it, so the model knows when the sentence starts and when it ends. So first of all, it has to know some position of each element with respect to each other. So there's one embedding, and there's a positional embedding, and the embedding would be position aware. So that is what the model wants to have. And if you put everything together, one next to another, we have this matrix of the position aware embeddings. So this matrix here will, be fed into the encoder, and you have the weight of the queries, the weight of the keys, and the values in the encoder. And each is multiplied by the query key and value, and with the activation, softmax activation function at the end. So you have this query with all these input elements, with the beginning to the end of the sentence, and it's multiplied by the transpose of the keys. Now, when they're multiplied, you have this new matrix, which is we call it QKT, and all of these values are the dot product. Now, the result of that is multiplied by the value matrix. Once you multiply it for each of the element, you have a weight, which is the result of the matrix from the query and the keys. So the result, the weight of the value is coming from the matrix of the Q, query and the key. And so you have a weighted average of values for each value, and all of them are a function of query and key. So that would be the encoder. Now you add a feed-forward network at the end of the encoder. Again, you have a context-aware encoded embeddings. So to summarize, you have an encoder, you have encoded embedding. Then the decoder's job is to start when it sees the beginning of the sentence or the beginning of the sequence. Start with the bottom of the stack is the self-attention layer. You have the encoder decoder attention layer, which, as I said, the self-attention layer job was, to look at what has been translated so far, all the words and that is the same thing as the masked attention layer. But the encoder decoder is look at the encoder at the same time while it's being decoding into the new language. So everything in the middle is being, looked at, and the attention layer is, looking at both the input and the output at the same time. Feed forward network and softmax layer, which produces a vector of probabilities to predict the next word. So the word A would be on, and so on and so forth. It gradually, the input, as you translate, each word that has been translated will be used as the input to the decoder. So this word is translated as predicted to be the first word, therefore is used as the input to the next iteration to the decoder. Again, this is done until it reaches the end of the sentence. Once it reaches the end of the sentence, it knows that it has to stop the process. So this sentence is translated into French at the end, and that would be it. Thank you for. I went over it very quickly because I didn't want it to, be a long video. But if you are, interested or have questions about it, let me know in the comments, and I'll try to answer them as soon as possible. Make sure maybe you need to watch it a few times. And right now, my channel has, by the way, has 1 subscriber, and my videos have about 12, 13 views. I think I'm making these videos not because of the views or subscribers, but I just want to give back to the community. Hopefully it's useful. And if I missed something or something wasn't clear, let me know. Take care.